welcome to this explainer. Okay, if the mere word chemistry instantly brings back nightmares of intimidating math or confusing textbook diagrams, I want you to wipe that slate completely clean. Today, we aren't looking at chemistry like some stressful math test. Instead, we're going to look at it as the ultimate blueprint for building the physical universe around us. We're breaking these concepts down from the ground up, so whether you're totally new to this or just here for a refresher, it's going to make perfect sense.
Here's our roadmap for this explainer. First, exploring the material world. Then, the language of measurement, rules of the microscopic, the mighty mole concept, and finally, recipes for chemical reactions. Let's jump right in. Section 1. Exploring the material world. Just look around you right now. Literally everything that takes up space and has mass is matter, and it mostly comes in three foundational states: solids, liquids, and gases. And you know, the particles behave wildly differently in each one. In a solid, they're packed in super tight, not much freedom there, giving them a definite shape. In a liquid, they've got a bit more breathing room to slosh around and take the shape of their container. And in a gas, they're just bouncing everywhere. But here's the really cool part to grasp. These states aren't locked in forever. They are completely interconvertible just by tweaking the temperature and pressure. Think about melting an ice cube into water and then boiling it into steam. The material itself hasn't changed its fundamental identity, it's just changed its state.
Now, how do we actually sort all that matter? Basically, we divide it into mixtures and pure substances. A mixture, like sugar water or the very air we breathe, has a variable composition. You know, you can put a little sugar in your water or a ton of it. Pure substances, on the other hand, like pure water or a gold nugget, have a fixed, unchangeable composition. But here is the absolute key distinction. Because mixtures are just physically combined, you can separate them using physical methods. Like, you can literally just boil the sugar water and the sugar gets left behind. Pure substances, they're chemically bound together. To break water apart into hydrogen and oxygen, you need actual chemical methods to snap those bonds.
Section 2. The language of measurement.
Okay, so to understand this blueprint, scientists worldwide need to speak the exact same language, right? We do this using SI base units, meters for length, seconds for time, Kelvin for temperature, you get the idea. But I really want to clear up a super common beginner mix-up, the difference between mass and weight. Mass, which we measure in kilograms, is the constant amount of matter in an object. It literally never changes. Weight, however, is a variable force exerted by gravity. So if you magically travel to the moon, your mass is exactly the same, but because the moon's gravity is way weaker, your weight drastically drops. In chemistry, we care deeply about mass.
Now, when we're measuring that mass, we have to talk about precision versus accuracy. Target practice is actually the perfect way to understand this. Imagine someone shoots at a target, and all their shots are grouped super tightly together, but they totally miss the center. Well, that's precise because it's highly consistent, but it's not accurate. Now imagine another shooter whose shots are tightly grouped right smack in the bullseye. That is both precise and accurate. In chemistry, hitting the true value is your accuracy, but repeating those results consistently, that's your precision. And you absolutely want both. Because chemistry deals with the entire universe, we run into some ridiculously huge numbers and some incredibly tiny ones. To keep from drowning in a sea of zeros, we use scientific notation. Now, please don't let the exponent scare you. It's literally just a highly efficient shorthand. Instead of writing out 20 zeros just to describe the molecules in a glass of water, we express the number as a simple digit between 1 and 10 and multiply it by 10 to a specific power. It's a game changer that makes handling extreme scales remarkably easy.
Section 3. Rules of the microscopic.
You might think that when you mix chemicals together, it's just chaotic, random magic. Actually, no way. Matter follows very strict, unbending mathematical rules called the governing laws of chemical combination. For example, the law of conservation of mass tells us that matter is never created or destroyed in a chemical reaction. It just changes form. What goes in must come out. Then you have the law of definite proportions, which states that a specific compound will always, without fail, contain the exact same proportion of elements by weight. Nature acts like a master baker who measures every single ingredient perfectly every single time.
So, how do we make sense of these laws? Let's look at Dalton's atomic theory from 1808. John Dalton basically gave us 4 simple steps. First, he said all matter is made of tiny, indivisible particles called atoms. Think of them as indestructible Lego bricks. Second, all atoms of a specific element are totally identical in mass and properties. Third, compounds are formed when these different atom bricks combine in fixed, simple ratios. And fourth, a chemical reaction is really just the reorganization of these atoms, like snapping the Legos apart and clicking them back together in a brand new shape. nothing is destroyed.
Section 4. The mighty mole concept.
Okay, here is the million-dollar question. If atoms are so unbelievably tiny, how do chemists bridge the gap between microscopic atoms we can't even see and the macroscopic powders and liquids we can actually weigh out in a lab? The answer is a brilliant little concept called the mole. And no, don't think of the furry animal digging in your yard. Think of it simply as a translator. In everyday life, if you want 12 eggs, you ask for a dozen, right? Dozen is just a word for a specific number. The mole is the exact same thing, just for a much, much larger number. It's a translation bridge that lets chemists scoop out a measurable amount of powder and know exactly how many atoms are sitting in that scoop. It perfectly connects what we count on the tiny atomic level to what we weigh on a normal lab scale.
So just how big is that number? Well, it's called the Avogadro constant, and it is roughly 602 sextillion. Yeah, 6.022 times 10 to the 23rd power. That mind-boggling number is exactly how many tiny atoms or molecules it takes to make up just one single mole of a substance. It really puts into perspective just how incredibly small a single atom actually is. Like if you had a mole of marbles, they would literally cover the entire surface of the Earth several miles deep.
Section 5. Recipes for chemical reactions. All right, with our materials understood, our tools sharpened, and our mathematical bridge in place, we're finally ready to read the blueprints and build some chemical reactions. This brings us to stoichiometry. Sounds intimidating, but it's really just a fancy word for calculating exact reaction recipes. Let's simplify a concept called limiting reagents with a super relatable bicycle metaphor. To build a standard bicycle, your recipe is 2 wheels plus 1 frame equals 1 bike. Now, imagine you have 4 wheels but only 1 frame. How many bikes can you build? Just 1. Even though you have leftover wheels, your production completely stops the literal second you run out of frames. In chemistry, that frame is your limiting reagent. It doesn't matter how much of the other stuff you have. The limiting reagent dictates the maximum yield of your final product. When we mix these ingredients into liquid solutions, chemists use a sort of concentration toolkit to track exactly how much stuff is dissolved in there. We're talking methods like mass percent, mole fraction, molarity, and molality. But molarity is especially interesting. It's calculated using the volume of the liquid. And since liquids naturally expand when they get hot and shrink when they get cold, the volume actually changes. This makes molarity totally unique because it's dependent on temperature. Understanding these little quirks is absolutely crucial for mixing accurate solutions in the real world. Finally, how do we know if we actually built our recipe correctly? Well, we can reverse engineer it using percentage composition. By breaking down a simple water droplet, for instance, we can calculate exactly how much of its total weight comes from each element. Since hydrogen is super light and oxygen is much heavier, water is always precisely 11.18% hydrogen and 88.79% oxygen by mass. Verifying this precise percentage allows chemists to check a sample's purity or even figure out the exact formula of a brand new, mysterious compound.
As we wrap up this explainer, I want to leave you with this fantastic quote by Nobel laureate Roald Hoffmann. He said, "Chemistry is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them." By understanding these foundational structural rules we've covered today, the states of matter, the laws of combination, the mole, we unlock the ability to combine a relatively small handful of elemental Lego bricks into the endless, beautiful complexity of the world around us. Chemistry proves that from a very finite number of building blocks, infinite variety is truly possible. You now have the basic concepts, the foundational rules, and the language to understand how the universe literally assembles itself. So I'll leave you with this one thought. What will you build with your blueprint? Keep exploring, keep learning, and I'll catch you in the next explainer.